Here we've indicated that these properties of the gradient vector can be proven just in terms of maximizing and minimizing the gradient function in terms of the angle theta. If we go into more than 2 dimensions, we don't have a single angle theta that defines our direction, and there's a different way of proving these properties. I'm simply going to assert right now that they do extend into 3 or more directions, so that in general, well, in 3 dimensions, the derivative of a function f of x, y, z is going to be just fx times ux plus fy times uy plus fz times, just about off of the paper there, fz times uz. Just the obvious extension. Now we can't write this in terms, again, of a single angle theta. We could write it in terms of 2 angles, but that would get somewhat cumbersome and would not be as easy to extend into higher dimensions. If we have a function of 4, 5, 6 or more variables, this definition can just be extended. We can simply keep adding. If the 4th variable is w, we can add an fw, uw. Again, we haven't proved that. When we come back and do this all rigorously in terms of epsilons and deltas, we'll see exactly how that works out. We'll just note a few things here. 1, u is now a vector in 3 dimensions. If we're talking about a vector in 3-dimensional space, a function, of 3 variables, then our values of x, y, and z are free to change in 3 directions, 3 independent directions of space. So our vector u clearly needs to be understood as a vector that specifies displacements in the 3 directions of space. So here u would be some vector which we might call ai plus bj plus ck. That's in 3 dimensions. When f is a function of 3 independent variables. Again, if f is a function of 3 independent variables, then all 3 of those variables are subject to change, and we need a vector in 3 dimensions to describe that change. The gradient vector is fairly obvious. The gradient vector is fxi plus fyj plus fzk in 3 dimensions. A convenient notation, vector operator notation, we define the del operator. That's like an upside down delta. It's got a vector sign over it. And that operator is the partial with respect to x times I plus the partial with respect to y times j plus the partial with respect to z times k. And we probably notice that we have a partial with respect to x and a partial with respect to y and a partial with respect to z, but we're not applying those partials to anything at all. But we are specifying that if we do figure out what we're going to apply this operator to, the partial of that thing with respect to x is going to be an I component, the partial with respect to y will be a j component, the partial with respect to z will be a k component. Well, this isn't particularly difficult to understand, I don't think, so let's look at it. If we have, hang on a minute, I've got an error here I've got to fix. I've written del equals, and what I intended to write was del f equals, because again we're trying to figure out what happens when we apply the del to something. Well, if we apply the del operator to a function f, and this is understood to be a function f of xy. I'm not going to write out the xy. Del f would equal what? Well, that would be partial with respect to x times I plus partial with respect to y times j plus the partial with respect to z times k applied to the function, to the function f. What does it mean to apply this thing to the function f? Well, if we just give this operator some basic algebraic quantities, some basic algebraic properties like distributivity and associativity, and I'm not going to be real specific about how that works out here. Your text will tell you a little more clearly. If we give this operator basic algebraic properties that we're familiar with, then applying this operator to this function is going to just say, okay, well, we're kind of distributing and kind of rearranging. Why not call that partial with respect to f times I plus partial of f with respect to y times j plus the partial of f with respect to z times k. This looks right, it feels right, so that's how we define it, especially when we see that, well, what does this mean? Well, this is just the same as what I wrote up here, and that's just fxi plus fyj plus fzk, the simple extension of the gradient that we considered in 2 dimensions. Again, it requires some proof to establish that this definition does extend from 2 to 3 and higher dimensions and makes sense in those dimensions. But for now, let's accept that it does, and everything works out just exactly as we expect. The gradient is it's not difficult to show that the gradient has the properties that del f evaluated at point xy is the direction of, let me back up, I have a correction to make here. I, without thinking, wrote del f of xy, and right now I'm trying to talk about del f of xyz. So let's go ahead and correct that. Smear it a little bit. Del f of xyz is the direction of maximum increase. Of the function f of xyz. Now that's evaluated at the point xyz, and to make that just a little clearer, let's say that's x naught, y naught, z naught. So we'll say that's at the point x naught, y naught, z naught. Using x naught, y naught, z naught to indicate a specific point where x, y, z indicates your general point. And the rate of maximum increase is the magnitude of the gradient evaluated at the point x naught, y naught, z naught, which equals square root of fx squared plus fy squared plus fz squared, where it's understood that fx, fy, and fz are evaluated at the point x naught, y naught, z naught. And we can also mention that the rate of maximum decrease occurs in the direction opposite the gradient and is equal and opposite, or the rate of change in the direction of maximum decrease, to say it properly, is the negative of the rate of maximum increase, the negative of this expression. So if it increases at this rate in one direction, then if you move in the opposite direction, it decreases, and its rate of change is the negative of the rate that you would have for maximum increase.